Monday, November the 16th, 2020. Physics 174, 8 a.m. Page 1. What are we doing today? On the agenda. Today, last regular class. Conservation of momentum. Technically linear momentum, but we'll just go with momentum. Wednesday. Exam number 3, multiple choice format. Like last time, maybe not as many problems though. Friday, makeup exams. If you have any, we won't know that question's answer until we get through Wednesday to see if you take exam 3 then. And next Monday, I guess it's November the 23rd, 20th, yeah, November 23rd. Final exam. And that's from 9 to 10:50 a.m. Eastern Standard Time. I have no idea what time zone you may be in when you're listening to this voice, but final is going to be on our time zone, which is, roughly, but not quite class time, but not class time. Okay, so it's going to be a little bit later than our normal class time, so we get to sleep in. Hurrah! All right. So also today, probably no office hours. I got 2 meetings this afternoon. Couldn't be helped. You can try to join in, but I don't think I'm going to be there. Email me any problems you got. Email me any concerns. Email me a couple of problems if you like, but don't mail me all the problems. I'm going to get back here. Very, very busy. You got to get all these exams finalized and proofed and online. Yeah, it's quite the task. All right, so let's do momentum. Let's see, where do we leave off our notes? Right here. Consider a collision. Between 2 objects where the only relevant forces to be considered are the forces that the 2 masses exert on each other during the collision. I've already talked about this. I said we could talk about the net forces acting on an object, and in the event of a collision, you can disregard forces such as gravitational force, aka your weight, friction, etc. Car accidents are very violent, so when you get hit by a car, you're only worried about the force the car is providing onto you. And if you're in another car itself, if you're in the other car, then you're worried about what the other car is doing to you. Gravitational weight has very little to do with anything during the collision. It's only a brief moment of time, but there is one overriding force, and that's the force of the collision. And so once again, this is during the collision. And that's why when we keep talking about this, we say, oh, this momentum conservation is good. That's always true, but we can only mathematically represent it easily during the collision when we can ignore all other forces. We just consider the force of the collision happening. So initially, I was kind of getting cramped there. So initially, this is immediately before the collision. We have the objects looking like this. We have mass A coming in with its initial velocity. And here comes good old mass B rolling in with its initial velocity. So during the collision or at the collision, these guys hit each other. And when you hit something, you'll find out your trajectory, your velocity will be changed. In other words, there's been a change in your velocity, so there's a change, there's an acceleration, and you only have acceleration if there's been a force applied to you, which shouldn't be a shocker. You run into something, ow, you know, it hurts. It's something's applied a force to you. So when these things interact, aka collide, you have B feeling a force on him. This is a force of A on B. And you got the force of B on A. I'll throw this up here right now. Monday morning. Suppose that in this case, speed initially of mass A is greater than the speed initial of mass B. And mass A is greater than mass B. In the context of this, in this context, which is larger? The force that A applies on B or the force that B applies on A, and just magnitude. So you can compare the numbers. Which one's bigger? Get ready to put a little bigger or equal to or greater than less than sign here. So we got F on B, some space here. So which is it? Which one's bigger? Which one? Not quite. We got A on B. We think it's going to be FA on B. Not quite. So it must be. Want to go for double or nothing? Not quite. They're equal. And we know this. This can easily be true. We can have the inverse true. We can have one can travel faster and it has less mass. This is Newton's third law. You push on me, I'm going to push back on you with equal but opposite force. So if vectorially, if I wrote these with vectors, I had to put a negative sign here. But when I just talk about the magnitudes, I can just set them equal. So I know it's a fine point. seems like, but so if I wrote this as a vector, I'd have to write it like this. And that negative sign just means one points in the opposite direction. I tried to kind of draw that up here. But if I compare the length of these arrows, this length is 20 newtons, this guy's 20 newtons. It is pointing in opposite directions. So. But I know, this is from Friday, last class, that the sum of the forces equals, well, let's keep it as just algebra here. Now let's keep it as calculus, and I can always slip back. I can always slip back to algebra. So there we go. Change in momentum or change in t. That's that good old what we call related impulse introduced on Friday. And for this case, the summation, remember this is what I did on Friday, equals the one force the other object applies to it during the collision. And it's a little bit ambiguous here. I don't know, object, which one's it, which one's the object? Well, because they both apply a force, it's equal to each other. You can talk about MA feels a force from due to MB, and that's all he feels. He doesn't have to worry about his weight or friction or anything like that during the moment of collision. And MB feels exactly the same thing. He only worries about the force he feels from MA. And he doesn't worry about anything else going on. So we're going to replace this guy. So for MA, the sum of the forces equals the force of B on A. And that's going to leave. So B applies a force on me, on mass A. That's going to lead to a change in A's momentum. Baseball comes in, you hit it with a baseball bat. So the baseball bat applies a force on the ball, and the ball will see a change in momentum. Maybe it's going to be a home run. For MB, let's put that little A there for him. Sum of the forces on B equals A on B, and that's going to lead to a change in B's momentum. So A applies a force on B, it's going to lead to a change in B's momentum. But due to Newton's third, which I've already written up here, actually I'm going to rewrite that line right there. Force of A on B equals the negative force of B on A. Doesn't matter who's got the negative sign, just matters there is a negative sign there. I'm going to do a little substitution here. I'll put that term in there. Put that term in there. Let's look at the right terms in here. Change in momentum for B equals negative change in momentum for A. I'm going to move it all to one side. Just a little algebra here on Monday. And since the change in momentum, this is basically this delta t, you can think of it, is the time period for the collision. Well, the time period that mass B is undergoing a collision is exactly equal to the time period mass A is undergoing a collision. I mean, they're colliding with each other. So as long as I'm colliding with you, you're colliding with me, the delta t is going to be the same. so I can factor out. You know, math guys, I sure don't like when I see I'm doing this, but maybe I should have kept with the deltas, because then with the deltas algebraically it looks a lot, you know, they have notes give me that weird look when I start factoring out things dealing with derivatives here. D over dt, momentum for mass B plus momentum for mass A equals 0. As the force of A on B and the force of B on A are only forces to be considered. Nothing else matters during the collision. So they're only forces acting on the two masses. We're going to call that the system. Then momentum of A plus momentum of B equals the total momentum of the system. So if there's a collision between two cars, I don't care about what the bystanders are doing. They're just standing around, you know. Trees are standing there, people are standing there. I don't care about the things that are moving actually involved in the collision. All right, so that's what that basically just comes down to. It doesn't really make sense, but it allows me to write this last term as this P total equals 0. Or non-calculus. I guess now I'll slip it and make sure I write this as non-calculus, because that's what we're going to be doing with this momentum stuff for us. Non-calculus, delta P total over delta T equals 0. So what's the change in your momentum? That's just going to be, anytime we write a delta, it's just going to be P final minus P initial over delta T equals 0. Just about there. So how can this be? Well, the only way you can get a 0 here, for even if it's a collision short term, it nonetheless will take some amount of time to occur. So delta T is a non-zero number, maybe very short, but still non-zero. So the only way you can get a 0 here is if P final equals P initial we're about ready to box her in, guys. Last thing we'll be boxing, I think, for this class. I can abbreviate this and just call this P final PF equals P initial. I like to see initial first, so I'm just going to rewrite it. This little bitty equation right there is the conservation of linear momentum for a system. So remember, when it came to energy conservation, if I can look at a system, whatever that is, it's in a box, I box it in. I look at the springs, I look at the balls which are bouncing around, I look at things going up and down inclines, and I say, okay, I'm going to measure all the energy in the system. And then I close up the lid and I let it interact with itself, and I come back later on and I'll make the measurements again. I'll find out, well, some things have increased their kinetic energy, some things have lost, some things the springs no longer is compressed as much, or maybe it's more compressed. But when I calculate up the total energy, I'll find I get the same number. And that's what this very important little ending we found here result. If I can measure the momentum of a system at any given time, then it will always stay, the momentum will always stay constant. It will never change. it might be hard to measure the momentum of the system after so long. A lot harder than energy conservation, but during a collision, it's actually quite easy. Because why? Because we can ignore all other forces except just the collision force. So that's what this thing say. Now, it doesn't mean an object can't lose momentum. Just like when one object, if you get things tied to a string or a pulley, as one object drops, it loses gravitational potential energy. Well, the other guy gains it. So you got to look at all the objects in a system. You can easily lose momentum, but it just means somebody else is going to gain it somewhere in the system. And the common pitfall is, even though this applies everywhere, keep in mind this is usually applied immediately before a collision or explosion, and that'd be the initial momentum, and immediately after. That'd be the PF for a high speed in small time collision explosion. Momentum conservation will work for slow ones. It'll work all the time, but it just gets harder for us to calculate with it because we'd have to worry about other forces. You know, if it's a sudden big jolt, big collision, or a quick explosion, whether explosion is there, whatever kind are there, then we can just talk about immediately before, immediately after that explosion or collision. Sometimes people like, well, when do I know when do I know I have to invoke energy conservation? When do I know to invoke momentum conservation? Well, sometimes you can do one or both, but it's usually in energy conservation. The only collisions possible are with springs. We've seen things slide in springs, and springs, you know, expand out and push things around. But those are actually those are longer time. So if anything, if you're dealing with springs, that's probably energy conservation. If you're dealing with objects hitting each other without springs being involved, that's momentum conservation. That's the thing I always say. I mean, we never deal with springs and momentum conservation. I've never seen it done. It's just too hard. It's too slow for us. Because if you remember when we've dealt with springs already, we've had some frictional forces involved in them. And the very nature of this little derivation I did was we ignored friction because it's such a quick interaction. And you know, some springs can, that's when you'd be able to get away with it. The spring actually, it was so, you know, it had a lot of energy in it. Basically, it was you released it and it was boom, it was just gone. It, you know, snapped back to the original length. And you can consider momentum, I guess, but that's not what we see in our class. All right, so just the bookkeeping things that are moving in the example. Let's see one last one. Where's you hiding at? There we go. Types of collisions. So if you're doing things in the back of the book and they mention some terms, like, oh, what that term means. Well, perfectly elastic. And I'll put this title, always P initial equals P final. Okay, so that's for all, any one of these collisions, it always holds. But for perfectly elastic, kinetic energy initial equals kinetic energy final. So Ki equals K final. And this would be your total kinetic energy prior to collision. And this would be the final total kinetic energy. When does this happen? In the everyday world, red pen here. Never. Okay. Never. But sometimes we can approximate it to be true if told so. Okay. So you never assume this actually happens. And it actually does happen a lot, just not in the everyday world. Well, it does happen a lot in the everyday world, just not in what we measure. Nuclei are hitting each other right now, bouncing around, nucleons. They conserve total kinetic energy, otherwise they just stop. Okay, so that works, but of course we can't measure subatomic things in a normal everyday world. And that's the microscopic, well, really microscopic. On a macroscopic level, objects move around the solar system. Not without actually colliding with each other. They just get close to each other. We consider that a collision. Gravitationally, they get close. They affect each other's momentum due to gravity. And as long as they're not in contact, and vacuum of space, pretty much vacuum of space, this holds true. But so unless you're dealing with, like I said, microscopic world or on the size of atoms or molecules, or if you're dealing with things like NASA would with the planets and rockets going by those objects, then we never see this. So it's a term which we sometimes can approximate, assuming, and that's what the big word is, assuming it's perfectly elastic collision. Two billiard balls hitting each other, kind of close, but not quite. And the reason is when two billiard balls hit each other, you know they hit each other because you can hear them. And sound is energy. So kinetic, if this holds true, then you can't have any kind of other energy sources at all, or any kind of ways to put dump energy into it or transfer it around. And but you can approximate billiard balls sometimes. So you may do a pool ball problem in the back, or sometimes it'll say, assuming it's perfectly elastic, the net is the heads-up plate. You can also assume this equation holds, and it gives you a few more ways to solve for a little bit more stuff. So unless told, do not assume this to be true. Okay, heads up about that. Look in the back, and they'll say things like that. That's what they mean. So the type of collision we see in the normal world is, well, it's not perfectly elastic, then it must be inelastic. Inelastic collisions. And this is everyday world. The kinetic energy of the system initially does not equal the kinetic energy final of the system, so you couldn't use this equation for yourself. But you can do energy conservation. You could do total energy conservation, but you can always do momentum conservation, and that's how we have to solve the problem. But there's a special case. I guess it's my last definition for 2020. Excuse me. That's a perfectly inelastic collision. And that's when the masses stick together after collision. So anywhere from, you know, two tape balls sticking to each other, or two cars sticking to each other after collision, that's a perfectly inelastic collision. In other words, what happens is you have MA coming in with its initial velocity. Here comes MB in, its initial velocity. There's some kind of collision. Boom. So this would be your initial. And afterwards, your final side. So you have PI over here. And here's P final. But this would be this globby thing. And it moves off, not with V final A or V final B, but just V final. It's all stuck together. I guess it's my first time to write a momentum equation all the way out. So in other words, you have P initial equals P final. But that would mean, well, what's the initial momentum of my system? Well, what's the initial momentum of good old MA? His initial momentum is M VIA. And then I got to account for the momentum of the, excuse me, got some, caught my throat there. Mass B's momentum. On the right side, okay, now after they collide, I've just got MA plus MB. P final. Now, of course, this is a vector, so it means actually this breaks into two equations. Now, it could be three, but usually we're just 2D. This means MA, VI, I love the subscripts here. They just go, or the last day the subscripts go crazy. VIX, so we have the initial momentum in the X direction for good old mass A, plus the initial momentum of B equals MA plus MB. V final X, kind of going almost full circle. This kind of starts looking like a equation of motion. When we do a scorecard, we can break our, or Newton's second law, whichever way you want to, we can break our vectors into X components. And here comes the Y guy over here. So the Y guy is going to look exactly the same, except I'm going to write Y's instead of X's. Hopefully I get all the letters and the I's and F's in the right spot, though. So this, I don't mean that equals that. This whole equation up here breaks into these guys right here. That's it. All good for that? Yeah. No problem. Okay. There's many problems we can now. There's a worksheet online. I don't know if we'll get to it or not. They've got the answers. I'll probably just give you as many examples that I can give you. I think that's the best. And you've got those other ones, the answers there for you. More the merrier, right? Okay, let's consider I may have to write that out better for you guys. This guy, this first time I wrote momentum right there. For two colliding objects, yeah. Remember, the best thing to do is write down what initially is going on. MA, moving in with VAI or VIA, which are like the put it, doesn't matter. And you get go MB with whatever his initial velocity is. So his mass times his velocity is his initial momentum. His mass times his velocity is his initial momentum. And momentum conservation says we have to do the total momentum of the system. So we had to add his momentum and his momentum. That would be it. Afterwards, there's somewhere, eventually there's some kind of collision. I don't know if you got to do a fancy collision symbol here for me, or I do, but look, there's some kind of collision. And afterwards, you get some kind of final thing taking place where MA is moving off with his final velocity, and MB is doing his thing with his final velocity. So this is how you would do these problems. You say you start off with P initial equals P final, and this is total momentum for the system. And what that means is P initial of A plus P initial of B. So A's momentum initially, B's momentum initially before the collision equals, that equal signs your collision. What happens on the left before the collision, what happens on the right happens after the collision. P final A plus P final B. Of course, this usually is just the start of it. Like after that, you just start. I guess this was yeah, it's similar things. We'll have an equation going, and then we'll say, okay, well, it's like the work equation. Yeah, it was like work equals, F dot dr. Okay, well, that's nice. That's your math. But the next step, you're going to start write F delta r cosine theta or some other form of that, so actually get something we can actually work with. So doubtful the momentums are going to be given to you. What we're interested in usually trying to figure out what the velocities of those objects were. We'll know all but one, or maybe we can be off the math we like. So this guy immediately becomes MA, or initial momentum of A becomes MA, the initial A. Same thing for good old B over here. And then you got MA, B final A plus MB, B final B. If there are three objects, I guess I can write that. I don't want you to get the impression you only have two objects. Oh, you can have three objects. If three objects involved, what would B look like? I don't know why I called that B. Either. And what it would look like is you just add a new term. You add a term to the left side. That'd be, I guess, MC V initial C. And to the right, you'd add a term. That'd be MC B final. BC. Okay. So you could have as many terms as you want to. You can have 5 objects colliding, you can have 2,000 objects colliding. Of course, we're going to be dealing with like 2, maybe 3. You can get to 4, but after that, you're just killing yourself with the math. We understand the concept at that point. And remember, these are vectors. So I'm going to write what I wrote for that totally inelastic one last time. I guess that's in the last box. This implies you have to move in the x direction. It has to equal the initial, has to equal the final. P initial and the y has to equal the final momentum in the y. And P initial and the z, if we ever have it, has to equal. There, that's it. I think that's a good box to end on. So we have to break our vectors into pieces, x and y components, and we take them one at a time. The x components, the momentum for the x, the momentum for the y. think here. Let you catch up. One of these in action. We have mass, let's call it M1. That's why I called it when I drew it down. Is it 1,600 kilograms? Well, it looks kind of like a car. Initially traveling at V initial 1 equals 44.7 meters per second. I'll draw the units in there just once. Say, hey, look, they're standard units. While M2 has a greater mass, 2,100 kilograms. Initially is traveling at only 6.8 meters per second on the J-hat axis. So you can imagine this is a car accident about ready to happen. We have a slow-moving vehicle. Maybe it's legally slow-moving, but we have a slower-moving vehicle in the front. And behind it comes this guy right here, the fast guy. He's catching up, so he's going to rear-end him. So what's going to happen at that spot here? M1 catches up and collides with M2. Immediately after the collision, M1 is found to be moving at V1 final. And it's not a vector because I don't know which way it's pointing quite. Oh, I don't know it's I and there's X and J or X and Y components. I just know it's moving at 35 meters per second. At an angle of 80 degrees, and that's from our good old days. We measure it counterclockwise from the positive x-axis. How fast is M2 moving? Immediately after the collision. You know, once again, sure, friction will take a hold of it eventually and slow it down, or maybe the guy will step on the accelerator. Who knows what's going to happen? But immediately after the collision, before friction can have any, you know, it's such a quick interaction there. Only the force of the collision has to be considered, and therefore we don't have to worry about frictional forces. Whew, take forever to write that thing down. Like I said, I like to draw it out a little bit, get an idea what's going on here. So initially, we've got everything moving along the y-axis. M2's up here. Shouldn't say poking along, or maybe he's in a school zone driving safely. His initial velocity. And here comes good old M1 behind him. A lot bigger arrow here. The initial one equals 44.7 J hat. This arrow should be a lot bigger than that compared to that V1 initial or V2 initial. And then there's some kind of collision. And afterwards, we know the following. Center of mass reference frame, I guess, but that's what they call it, the standard reference frame. We're told that good old V1, mass 1, car 1 is moving at this speed at this angle. So let's just draw this guy in here. It's in 1. V1 final equals 35 meters per second. And that's his final angle. 1/2 is 80 degrees. Now, as far as M2, where's he going? Well, I don't know. I'll take a good guess in this picture. I guess we kind of think that the when they bounce off each other, M2 should be going down. He might be. I don't know. He's definitely going to be going to the left. I can assure you that. How do I know that? Well, momentum's conserved. So what's the initial momentum in the x direction before the collision? What's the initial momentum in the x direction before they collide? Anybody out there want to go with it? Want to go with it? No, you're right. It's nothing. It's nothing. They initially they have no momentum in the x direction. They have a mv. All the momentum is in the y direction. There is no momentum in the x because they have no x component for the velocity. Remember, momentum is mass times the velocity. So if you have no x component, you have no x velocity or x momentum. So these yahoos initially have no momentum in the x direction. Afterwards, they have to still have no momentum in the x direction. So this guy's going to the right. I can guarantee you this guy's got to be going to the left. He's got to be doing it. Now, whether or not he's still going up or down, I don't know about that one because initially all momentum is going in the positive y direction, but he could have negative y as long as his has got enough to overcome what that guy brings as a negative. So I'm not unsure about what's going to happen here, but I'm just going to draw an arrow like this. I don't know. I'm just going to draw him like this. I'm not going to hold myself to this answer whatsoever. I believe he will go to the right. So I'm expecting to find, what are we going for? The goal is to find V2F, the speed. And how do we find V2F? That's V2Fx squared plus V2Fy squared. You take the x component and the y component, you square them, you put them through the Pythagorean theorem, and that's what you get. So I need to get these two guys right here. And my guesses are fine to make as long as we back it up with math. I'm guessing this guy's going to be negative. And I don't know anything about good old V2 final y. It depends on how big that guy is. We'll find out. So to do this, I'm going to go back to that box right there. I mean, you can write it differently. I mean, it's a vector. You can do vector algebra, write momentum real concisely as you want to. But since this class, we're just probably trying to do it for the first time for a lot of folks, I'm going to run back to that box I just showed you. Here. Pi equals PF. I know. P initial in the x direction has to equal P final in the x direction. And this is total. Yeah, I said it won't be conserved for an individual. So a car hit, you're standing in the middle of the road, a car hits you, man, your momentum was 0. Now it's not 0 after you get hit. Right? But if we measure the momentum of the car and the momentum of you, and these are the two objects involved in the collision. We measure it before the collision and after the collision, we'll find out the total momentum still equals, it hasn't changed. It's still whatever the momentum, of course, it'd be the momentum of the car. The car actually would slow down a little bit. Since it hits you, you gain that momentum, right? But So this is always total. Always remember that. So what do we have? In this case, we've only got two objects interacting. We have mass 1, v initial x, plus mass 2, v initial x for 1, v initial 2 for x. My little subscripts get a little, you can jumble them around, and when you see you missed one, but you can always, it's all pretty good. It doesn't matter the order. Equals m1 v1 final x plus, try to keep it constant now, v2 final x. Whew. Wow, subscripts to worry about. Okay, so what do we got going on here? Well, initially our objects have no x components for the velocity. They're just big goose eggs here. I like those. But on the right side, we have m1, which is 1600, and we're told that it moves off with a 35 degrees. So 35 meters per second at this angle of 80 degrees. So cosine 80 would give us v1x. Just breaking things down to components like we did pretty much first of the year. So really we've come full circle. We're just breaking vectors into components and adding up their like components with this overriding rule here. Plus the other guy, v2 final x. Solve for v2 final x, you get hopefully negative 4.63 meters per second. So this is not our answer, but boy, it's halfway home. To get what we want, we need the components of the second mass, the second car, truck, whatever you want to call it, and of its final velocity, and we just found one of them. So, okay, if you can take that one, then you can do the next one. You know probably what I'm going to do. Do. I'm going to write exactly what I wrote up there above. Total momentum being conserved. I know that if I add the momentum up in the initial in the y direction, this has to equal the final momentum in the y direction. So if I had all my angles up here and cosines, I just swap them back to sines, but I didn't have them here. I just put in some zeros. So what do I got? I've got m1 v1 initial y plus m2 v2 initial y equals m1 v1 final y plus m2 v2 final y. So what do I got? 1600 from m1. And initially, before the collision, m1's moving at 44.7 along the y axis. So that's my initial y component for him. 44.7 plus m2, its momentum, which is his mass times how fast he's moving. He's the slowpoke guy. He's doing 6.8. And afterwards, I have 1600 times 35 times sine of 80 degrees plus m2's mass times v2 final y. Just a little bit of algebra here, although it's not as fun because I have a bunch of zeros over here, but nonetheless I can solve it. Just take your time. And you get up, I guess wrong. He doesn't move downward. This kind of seemed like he should, but he doesn't have to. So they're both still moving forward, but one's going to the left, one's going to the right. We've done the hard stuff. V2 final, the final speed of mass 2 is V2 final x squared plus V2 final y squared. So you plug in the dash box, guys. here and here. In fact, put it in negative, go for it. Make sure you get rid of it at the end. V2 final equals 15.3 meters per second. So we just come up with a way of getting velocities and speeds, as we did with equation of motion, just a different way of doing it. As a matter of fact, equation of motion wouldn't apply here. There is definitely not constant acceleration in this thing. Well, we can consider maybe the underlying force, but it's much better to cleaner to consider this thing as just a conservation of momentum calculation versus the equation of motion. Like I said, we can't do equation of energy. There's too many terms in there. We got things being hit, bent, deformed, sound, all kinds of stuff going on in life. All right, any questions about this guy? This is basically the basic guy. I mean, you can do this guy. You can roll through them all, but let's do some more. Let's see we can do that guy. I wish we could have done Superman. We cannot, alas, we cannot do Superman. Not enough time. It's actually from your worksheet that maybe it's justifiable because it looks different. We don't like different stuff. So if you got your worksheet, look at that. We're going to look at the one for the explosion. I think that's number 4. Ooh, there you go. There you go. Number 3. Yeah, I'm going to do a couple of these guys. Let's go out. All right, so you have an object, and like I said, collision and explosion can be handled the same way with momentum conservation. This guy's going to explode into 3 pieces. 2 pieces have equal mass and fly off perpendicular to each other with the same speed of 30 meters per second. Third one's got 3 times the mass as the other guys, and we'd like to find the magnitude direction of this larger piece in the active explosion. And a little note here to make it simple. Throughout the class, have one of the smaller pieces post-explosion velocity of negative 30 I hat, and since the other guy has to be perpendicular, the other guy of equal mass has got to be perpendicular to it. We can have him fly off along the y-axis. And just for the fun, let's put it along the negative y. And then we're going to try to see if we can get these answers here for a larger piece. So initially, explosions are rather dull to draw initially. We just got, wherever you want to draw it. I don't think that really illustrates the 3-to-1-1 ratio, but initially everything's just sitting here. So what's the initial momentum? Well, initial momentum just equals 0. Nothing's moving. And then there's some kind of explosion. And what we have is some explosion. Positive y, positive x. We're going to have M1 moving off this direction. We'll call this, I guess, V1 final. And that equals negative 30 I hat. Meanwhile, we have a second piece, negative 30 J hat, or M2. And we'd like to know what's going to happen to good old M3. Well, the drawing, like I said, doesn't matter, but you can take some good guesses what we expect. Initially, you have no momentum. And afterwards, we see 2 pieces taking some momentum away. One's got momentum in the X direction, one's got momentum in the Y direction. So M3, the last guy's got to add up his momentum, so the y correct, the y momentum, so that it's equal to 0. So I'm guessing good old M3 is going to be kind of moving upwards, and M3's also got to neutralize this guy's x momentum, M1, so it's going to be moving to the right. I'm guessing we're going to see good old M3 do something like this. It's just a guess. I guess half right, half wrong on the last one. So let's see if I can get this guy. We'd like to find out good old V3, the 3M mass. So 0 equals M1, what's this called? V1 final plus M2, V2 final plus M3, V3 final. Remember, M1 equals M2, so we're just going to call that M, and M3 equals 3M. And we're going to substitute up here, get rid of some of those M's. So I guess we should do this. PI initial equals P final, sorry, PIX equals P final X. So 0 equals M V1 final X plus M. Let's call it M1, M2 just for a second. V2 final X plus M3, V3 final X. Well, if I substitute in my M's, nothing really changes except for the M1, M2, and M3 go away, and I'm left with this. And my M's will cancel. You can divide everything out by the M's. And you get good old 0 equals V1 final X plus V2 final X plus V3 final X times 3 for the 3, and that 3 still standing there. And what do we got? Well, V1 final X is negative 30. Plus, this guy has nothing in the x direction after the collision, after the explosion, so it's a 0. Plus 3 times V3 final X. So what do we get when we solve for V3 final X? We move to 30 to the one side, we divide by 3. It's 10 meters per second. So that's part of our answer.
Professor?
Yes.
What happened to the masses in like the third step?
These guys right here?
Yeah.
Well, they're all the same. Well, I got everything in terms of M now, so it's canceled. I divide by M.
Oh, okay.
Okay. Usually the mass is going to be given to you, but that's why I made it vague like this. Sometimes they won't. I mean, you can, if you know one mass in terms of the other mass, you can cancel them out. But yeah, usually it's going to be like the other problem: 1,600 kilograms, 2,100 kilograms, stuff like that. So yeah, I got reached a little too farther for Monday. Page 15, but I haven't finished it, unfortunately. So I got my my X. You can probably guess where I got to go to now. I got to get that Y. So the momentum in the Y direction has to be conserved as well. So I go back to good old 0 equals M1 V1 final Y plus M2 V2 final Y plus M3 V3 final Y. I can combine a few little steps here. Okay, this M is going to be, we're going to call M1M, we're going to call M2M because they equal each other. And M3 is going to be 3 times the mass as the other two guys, so I'm going to just call him good old 3M again. Well, we can save a little trouble here. Back our diagram in case we forgot. M1 initially was all moving in the X direction. There is no Y, so he's got nothing. The second guy, though, does have something this time. It's negative 30 plus 3M times 3. V3 final Y. Tongue twister. And so the ends cancel again. And when you solve for it, you move the 30 to the other side and divide by 3 again. You get V3 final Y equals 10 again. So as far as the speed of good old V3 or M3, that's going to equal his x component squared plus his y component squared equals 10 squared plus 10 squared equals square root of 200, which is factor out 10. And as far as I go in my head on Monday, I think square root of 2 is like 1.4. Vaguely remember that guy. Let's see him enough. Yay. So the final speed, I guess, sorry, my bad. V3M, this is the final speed. I should put F. I mean, he wasn't initially moving at all, so I guess it kind of useless to say initial. So I got that 3 F tucked in there way too much now. So I'm drawing in red because I didn't initially have him there. And that's one of the answers. I guess the other answer was the direction. We'd like to know the velocity. In other words, we'd like to know the magnitude and direction to give us a full picture of what's going on velocity-wise. And so we know how we get that angle. If you know the x and y components, the final directional angle of M3 equals inverse tangent of V3 final y over V3 final x. In other words, your y component over your x component. And this guy is rather easy. It's 10 over 10. And that comes out to be 45 degrees. And the calculator is telling me the right answer. How do I know that? Because my x and y components are all positive. So I'm definitely a first quadrant guy. So momentum calculations actually get further redundant fast, but they're very important. It's the only way we can figure out the velocities before or after a collision, because we can't, like I said, use those equations of motion force. Do I have time to do the energy one? Okay. 9 minutes. Do it. Do it. Let's call it a semester. I guess that's how I handle it. We'll just unlike you guys, usually in the last few classes, you guys did the problems, and I did different problems in different classes. You guys did different problems in different classes. I cobbled them together. I guess I can go the other way and just I can do the problems and cobble what I say together. All right, this guy here looks like kind of really bad, but well, with the stuff we know now, it's easy to do these kind of problems. You got an object down here on a spring, and the spring gets compressed because we want to do something for us. And so a half a kilogram ball is placed on it. That's going to be your M, so it doesn't look much like a ball, but it serves the purpose of just illustrating what's going on where. And we allow the spring to snap back to equilibrium, and it launches the ball upwards. So the ball is sitting on it, it's not attached to it. The ball travels upwards 1.5 meters, where it strikes or actually passes through a hole in a table and strikes the second mass, this guy right here, and they stick together. After the collision, what's the speed of the two combined masses? Basically, it's a car collision problem. So Well, we don't have a collision until we get up here. Like I said, the spring here, that's not a collision. Okay, it's when we see springs, we should be thinking energy conservation. When I collide, I need to know. I mean, I can give it where you've got any one of those things are unknown. The initials, the finals, or you can solve for the masses. You know, you can see how far things move, and you can determine how big the mass was, M1 or M2 was, based on the final velocities and initial velocities. So any combination that's possible. But we have to have a collision, and to know that when that collision, we have to know something about the velocity, something about them. So we have to get the little ball up to the big guy here. So in other words, we need to find out need to do a two-step problem. Part one, find m's velocity as it reaches M2. Right? Now we're going to be accelerating this guy over a spring. We cannot use equation of motion during a spring because that guy is definitely not a constant acceleration. All right, because the spring constant is not a constant force. It differs with an extension. So we're going to have to work with conservation of energy. And then when we get to this, we're going to have a collision. When you have collisions, you should automatically be thinking, man, collisions, it's momentum conservation. Use conservation of momentum for collision to get the final velocity, put a little star here, of M1 plus M2, because they stick together. So that's that thing. That's that. Oops, I circled something you can't see. They stuck together, so they're going to be. That's your perfectly inelastic collision. Oh my gosh, we only got a few minutes left. How can we possibly do this as fast as it can't be done? Can it? Yes. Energy conservation is pretty quick, and momentum is pretty easy too. Why is it going to be easy? Because it's a 1D case. But it wouldn't be much harder if it were 2D. So we need so part one. Here's initial. This is going to be E initial. And then up here, this is E final, okay, just before collision. So E initial equals E final. Well, we can write all the terms out. On E initial, we have three terms. Kinetic initial, the object initially has a spring that's been cocked back and compressed, and nothing's moving. So there's no initial kinetic energy. We could talk about definitely about the spring energy in it. So initial spring, and this object is going to be going upwards. So we can talk about the initial gravitational potential energy. Just before it hits the mass, it's definitely going to be moving. Don't think it's coming to a stop. It's going upwards. It may be going up quite violently, or maybe almost ready to, maybe almost brought to a rest, but we don't know that. We definitely know it's possibly moving. And then we also have the final gravitational potential energy. No spring after it. Once it releases from the, once the spring it goes back to equilibrium and shoots the mass off of it, we no longer have any spring energy. So there's no spring energy on the right side. So it's 1/2 K, guess it'd be delta Y squared plus mgy initial equals 1/2 M, oops, be careful, it's M1, V1 final squared plus, I didn't call it M1 either, M1 G Y final. Call Y initial 0. Whenever I have something, I want to measure basically the difference in height it travels or how much it goes down. I always make the lowest guy 0. So this guy here is just gone. We're left with 1/2 times our spring constant, which is 1,000, times how far this thing was cocked, which was 0.2 meters, equals 1/2 times the mass of it, 0.5, V1 final squared plus 0.5 times how far it goes up. I gotta be careful, it goes up 0.2 plus 1.5. Not the whole thing there. 1.5 is above equilibrium, so it's got to raise the mass up to Y naught by 0.2 meters, and then it keeps on going another 1.5 meters. And that's great. Right into the page number. We only have one unknown there, and I'm out of time. But V final 1 equals 6.83 meters per second. That's the end of part 1 of it. I'm going to take an extra minute. To do good old part 2. Part 2, that's the collision. P initial on the Y equals P final on the Y. There is no X, so I'm just going to leave it, draw that in there. And what do I got? I got M1, V initial 1 in the Y plus M2, V initial 2 in the Y equals, and they're sticking together, so it's M1 plus M2, V final Y. The big guy's not moving initially before the collision, so easy, it's a 0. And we're just going to be left with 0.5 times the number we just got before, the final velocity, or if you want to, final speed in the Y direction for M1 is before the collision is, or well, at the end of the, when the spring gets it all the way to the top, is equal to the initial velocity of good old M1 here before the collision. I said I got a little tongue tied there. And there it is. Box in my last thing for this class. Ta-da! Oh. I mean, that looked like a horrible. I should actually, I should have done that problem initially at the beginning of the year and just said, okay, let's do it. We couldn't have done it. And now, sure, can't beat energy momentum conservation. All right, that's it. You guys have a good day. I'll see you hopefully on Wednesday. And best of luck to you. Woohoo! Here we go. The last Monday regular classes. November 16, 2020. Physics 174. 9:30 it was. Page 1. Proof of conservation of linear momentum. And due to time constraints, see scanned in notes. Derivation, if you're interested in it. But I think I should skip that and just say what the answer is. For objects undergoing a collision, Or I could say explosion too. I keep saying a collision, but we'll actually do an example of an explosion because it could work just as well, or just as easily, the physics law. Consider the total momentum of the system immediately prior to the collision. It's total. So we have, let's say, here comes good old mass A, and it's moving it. The initial A, and it is on a collision course with mass B. Didn't draw it so well there. So prior to the collision, this would be initial. So P initial equal P initial of A plus P initial for B. If there were 3 terms here, 3 objects got about to collide, there would be an extra term here. There's 4, there's 8, add 4 terms. Okay, but this would be your initial momentum before, or total momentum before the collision. After the collision, so some kind of collision, we're going to see good old MB moving off at some final velocity. MA is doing its thing, moving off at its final velocity. So P final would equal the final momentum of the system after collision, equals PA final plus PV final. And what we find out is we find, that's if you're interested, you can see the derivation. P initial total momentum before a collision or explosion equals final momentum, total momentum of the system. If you're standing in the road, the car comes up behind you, you initially have 0 momentum. The car's got a lot of momentum. After it hits you, so the total momentum of the system is the momentum of you plus the momentum of the car before the collision. After the collision, you're going to have a lot of momentum, unfortunately. A lot more momentum than you used to have. The car actually slows down a little bit. I hope no one's ever actually been out there in a collision with a deer or something like that. But if you have, you slow down right after you collide with that deer. But the deer picks up what you lose, or the object picks up whatever you lose. So the total momentum before the collision equals the total momentum after it. So you have to add up all these guys as the terms in here. So how many questions on the exam? I don't know yet. I'm aiming for 14. 14 questions on the exam. That's what I'm gunning for. But not set in stone yet. So in other words, now PI equals PF conservation of call it linear, like I said, just in case you're careful. If you do searches, make sure you don't get rotational momentum because it is conserved too, but we don't get to it. Which implies, this is really kind of traveling back to good old chapter 3 and 4. When we have vectors, we have to worry about adding the x components together and the y components, but we don't add them individually together. We add the x's, we keep them separate. We add the y's, we keep them separate from the x's and the z's if they're there. This implies p initial in the x equals p final in the x. P initial in the y equals P final in the y. And if we had a z component, we have to worry about what's going on with it as well. So, when we do conservation of momentum, these are the guys we work with. Usually it's just those two. And so in regards to the previous two masses colliding, we'll find out that P initial x equals P final x means equals the initial of mass A in the x direction plus the initial for B in the x direction and then you do the final and just change I to F. And really this doesn't do much for us. We still haven't got to the point where we can solve for anything. Generally what we're out to, our goal is, it's going back to chapter 3. We're trying to figure out the speed of something, velocity, speed. Maybe we can actually work where we can find a mass as well, but we can't use equation of motion. We don't have enough information, and probably you couldn't apply it anyway because the acceleration probably is not constant during the collision. It's a quick but nonetheless extremely complicated affair to discuss what happens in a collision. But momentum or conservation, we can actually do it. Momentum, which we found out on last Friday, momentum just equals generic momentum equals m times v. So if you want to know the initial momentum's x component of mass A, cuts, 3 subscripts, holy cow. You'd write ma v initial A in the x direction plus mb v initial B in the x direction. I'm just expanding these terms. Anytime I write momentum, I can write that as m times v, and that's usually what we're interested in. Ma v final of A in the x direction plus mv v final B's x component in the x direction. So we don't say that. And this is usually what we're actually going to do in every problem. We're going to be doing something like this, and then we're given stuff. We're given maybe all the initial velocities except for one component. We can solve for that component. Or we could be given all the velocities and maybe one mass, and we solve for the unknown mass. I mean, you can have a collision, you can figure out how big the object was based on how far it moved away, or how its motion after the fact, after the collision. So that's this guy. And if you had to worry about your initial, your y components, and usually we do, the z usually gets left in the cold, but at once, due to pi in the y direction equals p final in the y direction for our two objects. You're going to be left with ma viay plus mb viby If it looks like this, it should. I'm just looking right up there and copying it down, except that instead of writing X, I'm writing Y. MA B final AY plus MB B final BY. So this gives us a way to find final components of an object's velocity after a collision, or before, depends on how much information is given. Common pitfall in all this. Keep in mind, usually, as far as we do, it's always applied immediately before a collision or explosion. And that's what we call the total momentum before the collision. We don't care about what happened an hour before the collision. It literally is right before the collision. The collision is going to happen 1/billionth of a second from now, because with all that known, there won't be time for any other forces like weight or friction to slow down or to change what the initial momentum is going into the collision is going to be. And immediately after, it's going to be P final, a high speed, small time collision or explosion. The usual problem we come across these using the momentum conservation is, when do we use it? I mean, it always applies, but when can we actually, be able to use it, mathematically, where it's simple enough for us to solve for it? And what the big flag should be, the red flag should be, this is a momentum problem, is there's been a collision happen in the problem. Something's hit something. Or maybe explosion. There's been some explosion. These are very quick processes. And we're trying to figure out maybe the velocity of one of those pieces before or after that collision explosion took place. Okay, so that's usually the red flag. We're looking for something to apply that looks something like this. Like I said, so we got some kind of collision explosion, and we're usually trying to find speeds, at least components, maybe velocities, or we could find the mass after or before that explosion or collision. This is the only time we ever see really, short-term high-speed collisions. And when I say high speed, I'm talking it could be cars. It could be two players in football hitting each other too. That's a high-speed collision. It's 1 second they're staying, the next second they're on the ground. It's a collision is a very, very quick event. There are places though where we see something that kind of looks like a collision. It is a collision, but it's not one where we would want to use conservation of linear momentum, because it's got too many terms tacked onto it. And we got to be careful about in energy conservation. The only collisions we can handle are with springs. So we've had things hit a spring before. But if you think about you watch something run into a spring, or even now a dart gun, if it's a stiff spring, it can shoot pretty fast. But generally, these guys interact over a longer time. So in a nutshell, if you see a problem, you got a spring in it, that's energy conservation type problem. If you don't have a spring, but something else is colliding with something else or exploding, then that's a conservation of momentum problem. You can do either one with either one of the formulas. I'm just saying what we can do, it's easy for us. If we deal with the spring for a conservation momentum problem, sure, we can do it. It will still be maintained conservation of linear momentum. But it's such a long time happening, you got to worry about what friction is doing to the event. Remember what we did on Friday? We said that in the event that the collision, there's one overwhelming force which can be considered to be acting on the object, and we don't have to worry about weight or friction. We just worry about that basically the force due to the collision. If you have a long-term event, you can't say that. So that's why we, like I said, it applies, but it's going to be more difficult to do it. So when it comes to this guy, all we got to do is worry about the initial momentum before and after. We don't have to worry about what friction's doing or how it's robbing from the system or vice versa. Vice versa is what it's doing. All right. So with that said, there are a couple types of collisions. They're given names. If you look them up in the back, you're trying to do problems. That's good. You're trying to do extra problems. They'll sometimes throw those terms at you and you think, wow, what's that mean? Obviously, it means something. They give it a name. Types of collisions. There's two basic types. In all cases, momentum is conserved. Okay, but we just have a few extra things we can tack on, and we know if we're going to know what kind of collision we're having there. Drink a tea. Okay, the first type we see is perfectly elastic. If a collision is perfectly elastic, then initial total kinetic energy, have you written as Ki, equals final total kinetic energy. Gotta stress the word total here. If you look at, when it comes to momentum, it's always total. We can break it apart into separate pieces if we want to, but we start off saying it's the total momentum, which is conserved. Individual momentum is not conserved, but due to the fact we know the total is conserved, we might be able to figure out the individual momentum or something associated with it if we're given enough of the pieces of the what's going on with the other pieces of the collision. So when it comes to kinetic energy, remember it's always going to be total. You get hit by a car, your initial kinetic energy is 0. You do not your final kinetic energy is not 0. But if it's for a totally or a perfectly elastic collision, if we add up the kinetic energy of the car, my kinetic energy initially, get a number, and then we somehow can make the measurement immediately after the collision, find my kinetic energy, find the car's kinetic energy, and they should sum to be the same. It would be the same number present there. When does this happen? In the everyday world, never happens. Sometimes we can approximate a collision to be perfectly elastic. But in general, the problem must tell us if this holds true, okay? Otherwise, do not assume it is true. So you're looking at a problem, and the problem will say, two objects collide in a perfectly elastic collision. And when that happens, whoa, I now know I can apply this equation right here. That's what they mean. If two objects collide and nothing's said otherwise, do not assume this, all right? Because it never happens in the real world as far as everyday world that we can measure. You can get approximately that with some things, and they, that's why if they do problems, they'll say assume it applies, and it's a type of collision we can see. The classic one is two billiard balls hitting each other. And it's still an approximation because you think, well, I don't know. I mean, maybe they look pretty nice. You know, it's a billiard table, it's a felt table, but you know, they worry about friction, what have you. Well, we have to worry about something that's taking the energy away from the system. So in the event of a collision, you can ignore friction. It's such a fast event. So during the collision, I mean, yeah, this won't hold no matter any collision. You give enough time, friction is going to start robbing you and start slowing things down. But during the brief moment of a collision, in a totally elastic, this could work. And you think, well, you have pool balls. I mean, you have pool ball. You hit a pool ball, and it goes different. But you can also hear the pool balls hitting each other. And because you can hear it, that means there's sound. And that means that that's energy being robbed from the system. So it may not be as much energy, and that's why we can approximate it. But the sound itself came from that collision. So a short time period, only the time period where there's a collision, you get the sound, and that's taking energy away from it. So even everyday world stuff, it's only approximate. When do we actually see it? It's crazy. It's microscopic. So as far as the range goes, it's microscopic. Nuclei striking each other, electrons bouncing off each other or getting close to each other and bouncing off, interacting with each other. Those are perfectly elastic collisions. And the electron doesn't bounce 5 times and stop. It just keeps on going. So collisions between subatomic particles are perfectly elastic. We, of course, we can't do those kind of calculations here in the everyday world. But you can go to the other regime. You can go from the microscopic to the macroscopic. We talk about objects in our solar system. We don't talk, when we talk about collisions in astronomy, we don't necessarily mean actual physical contact. They just get close enough where they can interact gravitationally, and they will affect each other's velocity and hence the momentum. So we talk about sending a space probe by a planet to get a little gravitational boost, or an asteroid zipping by the Earth, you know, misses us hopefully. Then those are actually easily modeled to be perfectly elastic. There's nothing to take away the energy from the system. There's no frictional forces in space or very little drag. As long as it didn't hit the other planet, then the kinetic energy will equal the kinetic final. But like I said, those are things which aren't, they affect us in the everyday world, we can't measure. We don't usually go out and measure, you know, the asteroid going by Mars. We don't usually go out and measure what happens when that neutron bounced off the proton. Nonetheless, it makes up our everyday world. Right, so that's one type of collision. Just be careful. Like I said, don't ever apply this unless it's told to you. Bad things happen otherwise. You can imagine you're using an equation which you shouldn't be using, and all goes wrong. The other type, which is the ones we do see, inelastic collision. K initial does not equal K final. And we see this in the everyday world. A special case is the perfectly inelastic collision. In this case, the masses stick together after the collision. So before, it just makes the math a little bit easier for us. Skipping back to these two guys interacting with each other. So A and B strike each other, and they move off with their individual final velocities. Well, if they're stuck together, they're going to move off with the same velocity. So instead of having 2 terms, and the final portion will only have 1 term, the combined masses and the final velocity of both. In other words, if you had something like this, so here comes mass A moving its initial velocity. Here comes mass B moving its initial velocity. Some kind of collision. And what's left, so this would be, I guess this would be your initial. I should say it first. This would be P initial, which would equal, let's write it, P initial 1 plus P initial 2. And after the collision, we're going to see MA plus MB stuck together. These guys moving off at some final velocity. So this guy's going to be, excuse me, PF equals M1, oops, not M1, M2, but MA plus MB, P final. So in this case, I guess I can just write it all down here. For this two-body problem, if there's 3, we have an extra term. We get MA PAI plus MB, initial velocity for mass B, equals MA plus MB P final. And of course, we had to do the same problem we did before, the same concept. We had to break this down into its X components and Y components and solve for whatever we need to. Example coming up in the class. I guess that's the last thing, the box in. Wow. So in summary, initial momentum, this is the total momentum of the system. And it sounds kind of funny, like, what do I mean by system? It's whatever's doing the colliding. If you got 2 cars hitting each other, I need to know the mass or the momentum of the car 1. I need to know the momentum of car 2. That's my initially before the collision happens. That's my system. If there's 3 cars striking something, 2 cars hitting a tree, I guess the tree's not going to be moving, but 2 cars hitting a third car, let's say, then my system are the 3 cars. It's what's doing the colliding or what's doing the exploding. I don't care about people standing around watching the collision. They hopefully not be standing there. They should be helping. But anyway, I just care about what's the things which are doing the colliding. That's my my system. And this equals, I guess, still momentum of the system prior to a collision. And this is the total momentum of the system, I should say immediately after a collision. Okay. Which implies, all right, one more time. I think I probably alluded to this. Your initial momentum in the X direction equals the final momentum in the X direction. Your initial momentum in the Y direction equals the final momentum in the Y direction. And your initial momentum in the Z direction, if relevant, is your final momentum in the Z direction. That's the last time on the box for this class. this semester as far as information. That ends chapter 9. What I have to do now is do some problems. There's a packet online. I'm going to do some problems in class. I'll go over a couple of the examples in the packet, and I'll leave the rest for you to do if you'd like to do some more work on it. Otherwise, you can do the suggested problems in the back of the book I got in the syllabus. So. Yeah. There's an impulse problem, actually. I haven't done one of those yet. So we get a baseball traveling at a certain speed or velocity you want to horizontally. Do number 5. Yeah, we did the other class we did. Well, I'm going to do we did the other class we did 3, so I thought I'd just skip ahead and do 5. And I'll patch them all together, all the solutions there, or most of them. A baseball's traveling horizontally at this speed, and I really say horizontally, but when you think of baseball going toward the bat, it's horizontal. That weighs this amount or has this mass, and if we swing it so that the ball and the bat are in contact for a very short amount of time, after the ball is traveling, we see it traveling at this speed at the end. Now, the direction, what's the average force acting on the ball due to the bat? Well, what do we got here? Stop and take a drink time. It's time for me. Force equals delta P or delta T. Delta P change momentum. So it's just gonna, you bet. So yeah, remember, anytime we have a delta, it's P final minus P initial. Technically, it should be vectors. I guess I should keep them as vectors as such. But if the ball is considered to be traveling horizontally, and when I typed that in here above, and the problem I did a horrible job of not stating that. Because of a travel angle we have to worry about. Yeah, I know you're thinking, well, the ball is doing a little bit, it's definitely traveling, probably not horizontally exactly, but we're just going to approximate it to be so. And why I can get away with that is because I'm just going to find the average force. A name I hate to use, a word I hate to use, average. But the force, if we recall what I did on Friday, this is the best we can. At least it's only an average, but it's the best. It's better than nothing. So what do we have? Well, we have the mass of the ball times V final of the ball minus mass of the ball times V initial of the ball, or delta T. And this guy's going to be let's see, you can factor out the mass of the ball, 0.145 kilograms. What's in it, or the final velocity of the ball? Well, if we consider positive x this way, this is the picture of the ball this way. Here's the batter up here. Then this is the initial direction is going to the right, so the final direction is going to be going to the left. So it's to be negative 49.1 I hat, because it's horizontal, give or take. And then we subtract out the velocity of the ball initially, and that was 40.2 I hat. Just divide by your time. It's going to be negative 18,000. 500 I had. That's newtons. Well, I say here the answer is in the 18,500 newtons in the direction the ball travels. After the collision, the ball's traveling in a negative I-hat direction. So that was a win-win for me. That's a big force. That's why you don't want to get hit with a baseball bat. So you can. Momentum allows you to find force really fast. Sure, it's an average. Don't like the word average, but it at least gives me something. Otherwise, I had to do Newton's second law, and I couldn't do Newton's second law. There's just not enough information given for me to solve it, but I could do it for that guy. So that's problem 5. Let's see what I'm trying to.